All right, let's go ahead and get started. Today we're going to talk about linking, which will bring together how compilation, well, basically how the whole compilation process occurs, aka how do we go from your source code down to actual binary code and all the other functionality that is helpful. Yes, no, it sounds like you want to add something, so I'm just, no? Okay, all right. Afterwards, I'll go in and again review Lab 5 so we can get a better picture of what's going on. Keep in mind that for Lab 5, you will definitely need to review the video because there's a lot of little things here and there that we probably have not fully covered about Lab 5. But yeah, let's go ahead and start talking about linking. This is the process after your code has compiled to an object file. The linker is actually going to sit down and try and paste it all together. And there turns out to be a lot of problems with that, and we will investigate each one of them.
There are problems?
Are there ever problems in computer science?
No.
Isn't that all we do? We just solve problems all day? Is that it?
Problems in computer science seems incompatible.
So, these were taken from Underwood.
Okay.
Why do you say that?
Because whenever you take it from someone, there's always something messed up.
Oh, well, I'm glad you think my slides are perfect. That's beautiful. All right, so on the left you have one file, and on the right column you have another file. So if you were looking at just the first example, and that's one file, you have int x, and then you have p1, and then over here you have not int x, and you have p1 as well. When you try and link the two together, what do you think is going to happen?
Sadness.
Why? What sadness will occur?
Because it doesn't know how to link them. It doesn't know how to link the thing, because there's a double on one of them.
No, just up here, the top
just the
line.
two.
Not all this,
Far.
just the top line.
Because there's more than one P1.
There's more than one P1. So if you called P1, which function would you be calling?
It doesn't know.
It doesn't know, so this is actually an error. Okay, how about the second one?
You got a couple indexes, so that's probably a problem, right?
That can be a problem, right? If P2 tries to use X, which X is it using?
Who knows?
Well, in C, the word static would be implied in front of int x, so it would be using the x inside of its file. So the C compiler wouldn't give you an error here, but other programming languages may give you an error because you have a variable with the same name in the scope. All right, how about the second one? Oh, that's fun.
You got int and double, so
Well, which one is x?
well, that's the thing.
I don't know.
Yeah, this one can throw an error as well, depending on the situation. What do we got down here? Oh, the only difference here is we set the numbers, and so we'll go into the specifics of what's going on down on these three, because I don't think we've covered those too well in our previous courses. Okay, so usually, or so far, we've talked about, or when you've used GCC or tried to compile your code, you have your C code, which is some ASCII source, aka text. You send it through some translator, and we so far have called it a compiler, and it produces a binary executable afterwards that hopefully you can run.
Hopefully.
Hopefully. Well, the problem here is that if you have a huge file, it requires a very large recompilation here. And it's also hard to be modular because you're putting everything in one file. And the point here is to fix this is we use something called static linker. Now we did this a bit in data structures because you had more than one .object file. In Java, you notice how we had more than one Java file. We didn't just put everything in one file. So we've already kind of solved these problems or talked about them in previous courses, but we're going to talk a little low level about how this is actually being done. So yeah, better scheme here is you take your .c files, .java files, and you translate them to a .o. In Java, they would be called .class files. And then afterwards, once you have all your O files, in C, you would put them to a linker, which would then produce a binary. In Java, it does the linking during runtime when you try and execute it. But at some point, the linker has to sit down and actually paste all your object code together to actually start executing something. So what we're talking about here is this linker down here. Okay. This is probably going to be one of the most important parts to understand. When you do GCC, it's not doing just compilation, it's doing a whole bunch of things for you. And that's why we call it the compiler driver, because it's kind of batch processing a lot of different operations together. So if you were to actually do -v with GCC, it would tell you everything you're doing. So first off, you have CPP, which in C is the C preprocessor. You remember all those pound includes, pound define and whatnot. It basically expands that into actual C code. That's what happens first. Afterwards, it actually runs the compiler where it takes that C code after the preprocessor and spits out assembly. That's all a compiler actually does. All a compiler really does is take your code and spit out the assembly file for it. And we've worked with an assembler where you have assembly and you can actually produce a binary. So the compilation step is just text to an assembly file. So it's actually just text to text is what it is. But it's an assembly file, so hopefully it'll be easier to translate. Afterwards, you run your assembler on that assembly file to produce an object file that is a binary representation of your assembly. And you do that basically for every .c file you have, or .java file. And then afterwards, you finally run the linker, which takes all your object files, the binary code that you've compiled for each file, and tries to paste them and link them all together into one actual executable, and then you can run it. Okay, you see how this is actually broken up into multiple steps, and there's not so much of a, it's not just compiling, it's actually multiple things happening at once. Okay. Here's a good question. Which of these steps do you think is the hardest? It's actually considered the second most hardest problem in computer science. How hard is the pre-processing? You're just kind of pasting code into one giant file, so it's not too bad. Translating your code, your English-like code into assembly. And we're going to add optimization steps, so you must optimize it for the architecture that we've just talked about. Yeah, bless you.
Sorry.
It's okay. How do you think that one is, Jackson? Sound like you have an idea.
That sounds tough.
That sounds tough. All right.
Sounds like sadness.
How about the assembler, taking the assembly code and just translating into machine?
Not that bad.
Not that bad. You gotta hook up some labels and whatnot, but. And the last one's a linker, where you have to take all your object files and make sure update all the pointers so they're pointing to the right things, and then dump it into a final binary. There's some pointer arithmetic. You can get a little hard there, but it's not that bad.
So
The compiler which is considered the second hardest thing in computer science, of translating, or at least from my research, the second hardest, I should say. Translating your English-like code into an optimized or somewhat optimized assembly code is the hardest step. Everything else is really just there to take the load off the compiler, because this is really hard to do. Okay. So we're just talking about the linker today. What does a linker do? You have your object file, your machine code. It's going to put them all together into a single executable so you can load it when you execute the program. Good morning. When you're merging everything together, you have to resolve all the external references. You know, which X variable is this? Is that this guy's X variable or someone else's X variable? Are you loading in some type of library? You need to link that up as well. Yeah, that's where relocation of symbols comes in. Let's see where we go. Update all references. So here you have a reference to symbol A, a reference to symbol X, but A may be something else in another file. hopefully they don't merge or have any problems when you use them. Okay, why a linker? Well, the real answer to that question is you're trying to take the load off the compiler. The compiler does one thing, translates your English-like code to assembly. The assembler does one thing, takes your assembly, translates it to a binary machine code, and your linker is going to just do the one thing of taking all your binary object code and putting them together in a final and packaging. It's really a packaging it together so you can execute it. Is probably a better way of explaining it. The other point here is that you have your code, that's an object file. You may now use another library code that's already been compiled. You don't have to go and recall the compiler, which we just talked about was a really difficult step. You just have to link it in and basically copy paste the code and set up your pointers so it's correct. Efficiency-wise, you only have to change your source code. You don't have to recompile your libraries or other source code. Space, libraries can be stored as a single file in the operating system as opposed to inside of your program. Okay. So how are they stored? There are different formats to store your executable, and the formats are operating system dependent. So this is a software operating system dependent file format. You're going to go into a lot more depth about this in operating systems. You won't have to, so don't worry about it, which is fine, but do be aware that there's different formats for every single operating system. What we're going to talk about here is ELF, because we've been working with Linux, and that's the executable and linkable format. It was derived from System 5 Unix, which is where a lot of NIX operating systems derive a lot of their functionality from. And it's been adopted by BSD as well as Linux. So you have one format for object files, executable, shared, so forth and so on. And just so you actually can see what we're talking about, let's see, what's a standard program we have in? Okay, let's go and locate Vim. Wow, that was big. Let's grep for bin. All right, so we do file user bin Vim. Symbolic link to that guy. All right, so let's see, alternatives Vim. Another symbolic link. I wonder how many of these we're going to have. File user bin Vim GTK. There we go. File inside of Linux tells you what type of file it is. So there are a lot of symbolic links, which just is jumping from one file to another. But as I went through all the links, I finally got down to what it is. Let me clear the screen so that's easier to read, because that's hard up there. But yeah, we're still using ELF, executable format, 64-bit, shared object. Hey, look, it's still System 5. Dynamically linked, which means its libraries are going to be loaded in by the operating system and not compiled directly into the binary. There's an interpreter to help load it. It's for GNU Linux 2.6.32 or higher. And it looks like it stored a build ID. And it's been stripped of any extra symbols, which is just a way to make the binary smaller. Because when you do debugging, you add a bunch of symbols inside of the final executable in order to help you debug if there's any problems. But when you're done, you want to take those variables out because you want to make your executable as small as possible, and that's what it means by it's been stripped. It's been stripped of any extraneous information. Okay. Oh, good. We're going to have a picture. If you were to open up this file and start reading the binary, it's going to look something like this. The first section is the ELF header, which tells you that it is an ELF file. You might have some extra table that tells you about how the program is loaded or any extensions it needs. The text section is your code. That is where your binary stuff is stored, aka your assembly is put inside of the text. The data section is any part of data that needs to be loaded in and for the program to use. Let's see, BSS, this is for any static data. You may have any type of global. All right. And there's other symbols here. I'm going to breeze over this because. Good morning, Jonah. Thank you for coming. I'm glad you woke up today.
No, sorry, I had to take my mom to work today.
I'm going to breeze over some of this because we're going to go far more depth in operating systems, and it's not that important right now. All right, symbol tab. We're going to go through debug. All right, example C program, m.c and a.c. All right, let's go look at this. What's going on here? Ooh. Have y'all seen the extern variable name, or I'm sorry, keyword before? So when you put extern in front of a variable, you're saying that this variable is going to be defined somewhere else, aka over here. So when you compile it, it's going to put that in the information, but it's not going to know where that variable is until you link it, because that's when you're linking the m.o and the a.o together.
We do have to take operating systems.
No, you don't.
Dr.
We-
King sent me an email like a week ago.
Yep.
With the updated checklist. And it's still on there.
It will be removed.
Awesome.
We have already approved it for cybersecurity.
Oh, I was supposed to say.
Cybersecurity doesn't.
Excited.
Oh no, you're in no operating system is good. No, it was removed for operating because it's pure coding. Like this is actually not pure coding. That one is, and you're going to learn it all in cyber defense anyways. So there's no point. Okay. So extern E means at some later point we're going to link in the E variable, and then what does this next line do for those of you who took data structures?
Take whatever's at the address for EP.
Or not EP.
Oh, and
For the E.
Stores the piece of pointer.
EP is a pointer to a.
Reference in
Oh, okay, hold on.
address.
Hold on.
the address of E.
All right. I know you're thinking the right thing. Let's just make sure we state it correctly. What is EP's type?
Pointer.
A pointer to a integer. All right. So EP is going to be a pointer to an integer, and we're setting it equal to what?
The address of
E. E. Right. So EP is going to store the address of E. So we set x to 15. We create y, which I guess is just going to have some random value. And then what's happening with A?
dereferencing whatever's in
EP.
the EP, and then you're adding X.
Y. Right. So yeah. Any problems?
It's gross.
No, it's not. What's the problem?
Wise doesn't have a number.
Why doesn't it have a number? Well, anyways, let's see how this is done. So you are going to have some system code, which is provided by the operating system when you try and compile, and that's just to set things up. And you notice that with your Qt spim, how it executed a bunch of code before your program actually loaded. In reality, I'm trying to remember, like 100,000 cycles go by before your program actually starts, because the operating system has to set up a bunch of stuff. That's what this is. System code, system data, get that set up. Main.e, you have e equals 7, and then a.e right here. A.o, sorry. As a, let's see what this is trying to tell us. So you have your two functions, main and a, and then you have some system data from up here. Notice e equals 7, and then ep is at reference of e. The linker right here is what's going to actually set it up so that ep can actually point to the variable e, which is stored inside of main, or m.c. Okay, symbols are lexicographical entities, and functions are names and variables.
Sure.
Yes, but okay, that's not too helpful until you do compiler writing. All right. Okay, when you're compiling this, there's a symbol table that tells you where every symbol is located in memory. That's really all you need to know. All right. So it says, I mean, literally, there's just a table that says, all right, whenever you see E, it's pointing to this memory location here. You say EP, it's pointing to this. It's this memory location right here. So they can look up what the variable is, where it's pointing to, and then its type. All of this is references can either be local or external. Okay, here that's the one thing you need to keep in mind. Let's see, because R is R local or external? Local to
MC. Or main.
main inside of m.c. Right. E, that's kind of a trick question.
It's local to m.c.
Right.
But they
But
were
when it's
global.
in a.c, it's external.
It's global.
It's global.
Global. Right. Yeah, C gets a little weird. Reference to external A. Yeah. E is local here. Reference to external symbol exit. Oh yeah, that's a good point too. That's a system call. Or I'm sorry. C. No, it's. Oh, that is a Linux library call, or system call actually, and that is an external symbol. All right, another local reference, because these are local to the files. Reference to external symbol E, because you're making E be external inside this file when it's referencing that guy over there. All right, def local symbols X and Y. Okay, great. Local symbol A. It's local to the file, but you make it external when you're trying to use it here, because that's when you're trying to link it together. You should have inside m.c your definition of the function A, so it could actually know what needs to be called. All right. Wow. Yeah, we're not doing that.
All right.
All right, good. Whew. We don't need to go over that right now. All right, strong and weak symbols. Strong procedures and initialized globals, weak is uninitialized ones. So, oh, it's already been labeled. All right, why is foo weak?
Because it doesn't have a value assigned to it.
Doesn't have value and it's two things. It's not a procedure.
Oh, okay.
What was that?
It has not been initialized and it's not a procedure. Notice the procedures are strong. A strong symbol can only appear once inside the linker, because once it's been initialized or it's a procedure, you're basically saying in the global space that you are always using this symbol.
So it doesn't matter if it is if somebody does put it somewhere else, you usually use the first one.
Well, you'll
You'll
throw an error, like a redefinition error, is usually what C will throw. A weak symbol can be overwritten by a strong symbol of the same name. So the strong conquering the weak. If there are multiple weak symbols, the linker can pick an arbitrary one. Oh, does that sound dangerous?
Yep.
Yep.
That's a no-no.
All right, the rules aren't meant to be broken, but yeah, they can definitely cause some problems. All right, let's go back to this. What's the error on the top one? Now that we've talked about strong and weak. Well, X is not initialized, so he's weak. But what about the P1 and the P1 on the left?
Used twice.
And they are
Both strong.
strong, yep. Two strong symbols. All right, how about the next one?
X is under both weak, so it'll just pick one.
Yeah. It's not what you really want, but it's okay. All right, how about the next one?
Both weak, but they're different types, and if it picks one, it could be.
Right, so, whoa. Write to X and P2 might overwrite Y. Oh, yeah, that's a good one. Why is that? That's a good one.
Because
The size.
Yes.
Your-
So how many bytes are in a double?
Double and
Yeah, double float.
float.
Float is 4 bytes, so 8. Integer in our systems are 4 bytes each. So if you overwrite X, it may overwrite the X and Y over here, or it may overwrite that X. It depends on what the linker decides to pick. Hopefully the linker picks this X, but you can't necessarily
You can't.
guarantee it. So yeah, don't be doing this.
Sadness.
Sadness. All right, how about the next one?
Well,
The first one's strong.
yeah. So if you tried to write to X and P2, it's definitely
Writes to X will override it. So now that X has been a strong link, it's going to use that one, and it will overwrite the Y. So beforehand it might, now it definitely will. All right, how about this last one?
Now that you really want to say the information, we're going to mess you up.
Yeah.
First one's strong.
Yeah. Reference X will refer to the same initialized variable. Now what's this last one? Two identical weak structs compiled by different compilers will have different alignment rules. Yeah, that would be bad. Because one compiler may arrange the X, Y, Z in one format, and the other compiler will do it in a different format. Therefore, if you try and link the two, it'll be all over the place.
That doesn't sound fun.
No, it's not. Okay. All right, so we've talked about linker. Why are we using these linkers? So far, we've talked about being able to execute only a portion of your code and then link it together, which is great. But it's also useful to package commonly used functionality into some type of libraries. Math, I/O, memory management, string manipulations are very common. You could put everything into one source file and then link this big giant object in the end, but that would be space and time inefficient. Or you could put each function in a separate source code, and programmers explicitly link the appropriate binaries of program. More efficient, but now the programmer has an issue. So one solution is a static library. This is a .a. This is not a DLL yet. We're moving over to a DLL or a .so. Right now we're talking about a static library. This is something that has the bunch of object files all inside of one. So you might have a static math library, you might have a static GUI library, so forth and so on. The point is, since it's static, when you go to finally link it, that library is linked directly into your final binary. lib.c for all your C functionality, like printf, standard I/O, etc. So you just take that .a, link it together, and then produce your program. And this is very common for your standard C library calls. All right, you can create this by, after you've translated to a .o, you just call the archiver and you create a .a file. And that packages up into something that you can link together in the end. All right. Everyone see what's going on? The .a is really just a packaging of multiple .o files.
Ta-da.
Ta-da.
Who's ATO?
What's it?
I was just thinking ATOI, that was a change. to-
ASCII to integer.
Oh, yeah. I always messed up.
All right, libc.a, standard C library, 8 megs. Wow, that's pretty big. 4,900 object files. Does a lot of different things. What's that? Stuff. libmath, the C math library, about 1 meg. Does all your floating point. If you were to actually list them out, fork, fprintf, open, fscanf, hey, look all those functions you call, right? Math, same thing. Cosine, well, these are arc cosines, but all your functions over there. So the linker has to put them together. Okay, great. I hope we go to dynamic. All right, so I guess we're going to talk about how your operating system actually loads the binaries. You'll go into more detail with operating system, so I'll just give you a high-level view. All right, it's an L file, great. Maybe some header required for the executables to set up the program. All right, we do all that, that's great. We load the text section into memory. We load the data also into memory, and then we set up your binary, your static code space in memory as well, and then we start executing from the text section.
It's the same as the other
Yep.
diagram.
Okay, good. We are going to go with DLLs. So statics have a couple of disadvantages. If everyone's using libc or libmath, that means you're going to be linking in libmath or libc into all these different programs out there. But in reality, you just need one C library, right? Because you're just running the same code over and over again. So that's a lot of code in the virtual memory space, which is already a limited resource. Minor bug fixes to libc would require every application to recompile themselves. So instead we have something called shared libraries. These are DLLs in Windows, or .so for shared objects. And the idea is that instead of compiling in your library, you're going to tell the operating system to load the library when you run it. That's it. And this is extremely common.
Is that, so it's a time saver or?
A space
Space
saver.
saver.
Because instead of compiling libc into every program that's out there, you're only going to load libc when you're done. Now here's the other big advantage. You may have 30 processes running, right? 30 programs running. If you compile them in statically, each of those 30 are going to have a copy of libc inside of them. But if you do it with a shared object, you load libc in one memory space, and then all 30 programs just point to it because it's just code. It's not going to change, and it's not going to change is what it comes down to. You're not writing to it or anything like that. And the other advantage is that if you need to update libc, you just update the shared object file, and then you update everyone's program at the same time.
Right, if you did it the other way around, you would take up more space because you have the library with each one of them. It would be so it would be a little fast, but just not enough to make it worthwhile.
Yeah, the speed is negligible. And hopefully I will show you later on this course that it is actually slower to compile them into your binary. But we'll get to that. Okay. So here's the new architecture here. Again, you compile your code .os, send them to a linker, which produces an executable that also has libc, pointing to libc needs to be loaded. When you then run your program, the operating system takes libc, and if it's not already loaded in memory, load in memory. If it's already there, then you just hook up pointers to where those function calls exist. That's it. Okay, good. So, complete picture. Everyone take a step back. This is the point that this is what's important. So let's go ahead and run through this. There's a whole point of this talking about the linker. M.C translates it, which is preprocessor, run the compiler, run the assembler on what was taken out, produce a .o. Do that for all your .c files. Next comes a linker, takes all your .os that you created, and then any static libraries you may want to load in at that point to produce an executable file. If you have any shared objects, this loader, the executable will also say I need to link to these shared objects. When you go to run, notice here it's been compiled, you're done, you ship it to the customer. When you go to load, aka the customer is going to run your program, it's going to see if there's any shared objects you need, and it's going to link them in at that time. If they aren't loaded in memory, it loads them into memory. If they're already in memory, you just set up the pointers pointing to where they are, and you're done. All right, are we good?
Sure.
Sure? All right, great. And we will